So good morning, sir. This is me again, Jenny Encancados. Today I will present to you my own design of a separately excited DC generator. So first, let's understand the circuit diagram or the diagram. So this part, this is the uh, it is where the field windings is located here. Then in this part also we will know this is the DC source. So in order to energize a separately excited DC generator, we must have a source, which is a battery. So usually in a separate DC generator, battery is one of their sources. So in this part, the armature, so we can calculate the generated AMF here as well as the power generated. So this is the brushes. So brushes also have a voltage drop. So this is the armature resistance and the armature current. um, Here is the terminal voltage, the VL. And also we can calculate the power delivered here. So since it is in series, so IA is equal to IL. So and this is wounded by a lap winding. So lap winding is intended for a low voltage and high current. So this is the given parameters. So in the armature, there are 4 poles. Then the armature speed is 1000 rpm. Then the total number of conductors is 200, and the flux per pole is 30 milliweber. Then since it is in a lap winding, so we use the formula for a lap winding in finding the total armature current paths. So M times P, or the so since it is in simplex, so the multiplier is 1. So that's why our armature current paths is 4. So here we can also see the armature resistance and the armature current. So I give the armature current here in the DC separately DC generator is 150 amperes. Then the armature resistance is 0.04 ohms. And here we also have a brush drop, which is equivalent to 3 volts. So the first thing we must do is to find the generated EMF in the armature here. So in finding or in calculating the generated EMF, so we must use the Epson formula, which is P times N times Z times flux per pole over 60A. So since we have all the uh, given parameters, so we must simply substitute all the values here. So upon substitution, so we got a R now is our EMF, or the generated EMF, is 100 volts. So after getting the generated EMF, so here we don't know the VL, or the terminal voltage, so we simply use the KVL here in order for us to arrive the value of our load voltage or terminal voltage. So upon applying KVL, so E minus VB minus I times RA minus VL. So VL is unknown, so VL is equal to E minus VV minus IA times RA. So since we have now the values of the corresponding variables, so we simply substitute, then calculate. So the result of the line voltage or the load voltage is 91 volts. So since we have now the load voltage, we can also get now the power delivered here, the power delivered. So power delivered is equal to load current times the load voltage. So here, so 150 times 91, since our VL is 91, so our power delivered now is 13,650 watts. So since it is in series, so IA is equal to IL. So now we can also get the power generated in the armature. So the formula in finding the power generated is equal, PG is equal to generated EMF times IA. So 100, because our EMF is 100 times 150, because IA is equal to 150. So the power generated in the armature is 15,000 watts. So since we have now the power delivered, so we can also get the efficiency of the separately DC generator. So we can get the efficiency of this generator. So upon finding the efficiency, we simply use the formula, which is efficiency is equal to PL over PL plus P losses. So since we don't know yet the total power losses of the generator, so we must solve it first. So power loss is equal to PA plus PB. So since here in the armature, so we can say that there is a losses here, as well as in the brushes. So now we can calculate the power losses. So PA plus PB. So PA is equal to IA squared times RA plus IA times the brush drop. So simply substitute the values. So the total power losses in the generator is equivalent to 1,350 watts. So going back to the original formula and finding the efficiency, so PL over PL plus P losses. So our PL is 13,650 over 13,650 plus the power losses, which is 1,350 times 100% to make it a percent. So the result is 91%. So that would be all for my design of a separately excited DC generator. So thank you, sir.